Hi, welcome to again IV characteristics of MOSFET. In the last video, we have seen the IV characteristics of MOSFET, that is the output characteristics. Now, in this video, we'll see the transfer characteristics of the MOSFET. So, it is called as transfer characteristics because we are we are considering two parameters. One is ID, other is VGS. It is ID versus VGS at a constant drain to source voltage. Uh, This is my dependent parameter, this is the independent parameter. Since this is VGS here, this is at one side, and this is ID we are talking about, which is on the output side. Since it is on two different input and output side, that's why the term transfer. So it is transfer characteristics. So let us see how does this will look like, because we know that as per theory, if this VDS is applied, even if VGS, if it is not greater than the threshold voltage, then MOSFET is off. So till threshold voltage, ideally till threshold voltage, the transistor will be off. That means there will be no drain current. So once the VGS exceeds, so then this current increases. So this current increases in a quadratic fashion. So we know the expression for drain current both in linear and saturation region as given by, so ID will be given by half Kp W by L VGS minus VTO whole square if the MOSFET is in saturation. If it is in linear region, we know that ID is given by again half Kp W by L 2 times VGS minus VTO or VTH into VDS minus VDS square. So VDS square will be the expression. So this is the expression for the current in linear region. So it is half kpwl 2 times VGS minus VTO into VDS minus of VDS square. If you can see in the saturation region, the current is independent of VDS, whereas in linear region it is depending on VDS. So in this IV characteristics, so we are keeping this VDS constant and we are varying this. So let us see the simulation of this. So what we have done here is we have kept the value of, okay, let me just, okay, I'm just doing the same circuit what we did in the last class. So this is a MOSFET with Kp is equal to 100, VTO is equal to 0.4. I have chosen the W and length as mentioned here. This is VGS, this is VTH. Suppose if I do dot OP, I will get the DC operating condition, that is what is different voltages, nodal voltages and the loop currents. Suppose if I run this, you can see it will be listing what are the nodal voltages at different nodes and what are the current through different nodes. So looking at this, the drain current happens to be 200 microampere. Now since the MOSFET is in saturation, this current is okay. So even if you calculate, you'll get the same thing. Now in order to get this characteristics, so I have to keep a VDS constant value and I have to change gate to source voltage. So that I can do it using the dot sweep command. So for that, let me just go to this edit simulation command. Let me go to this DC sweep. This is a voltage source which I want to sweep. So let me name it as V1, and you vary from 0 to maybe 1.5 volts with an increment of maybe very small increment 0.01 for every 10 millivolt. Look how it looks. So this is the variation. Even though it is 0.6, it will be overwritten by these specifications. Now what will happen is I will be keeping this VDS as 0.8, whereas VGS is changed from 0 to 1.5 in steps of 10 millivolts. If I run it now, this is how it looks. You can see 0 to 1.5. Now I can trace the current. So one way is you can able to go over here and add the trace, which is IDM1, or I can do it in the schematic itself. So you can see here, this will give different voltages. This is the symbol of a probe, if you can see that red one, And if you want to find the current, so this is, you go near to the terminal, you can see this is the current. So this is the ammeter symbol which is indicating, if you can see the arrow indicates it's the current going into the drain, which is the drain current what we are looking at. This is exactly the same way as I mentioned over here. So this is my drain current which is going into, this is the current, so this is ID. So let me just go here and then find out what is that current. Now come here, then plot. You can see this is the characteristics. So till 0.4 it is 0. This variation is quadratic. This variation is quadratic. Now this is for different values of VGS. What is the drain current? What is the drain current? Suppose if you want to verify for a particular condition, maybe if I just keep 750 millivolt as VGS, so you can see, let me just note that value. For a VGS of 0.75 volt, I have a current of 612.5 microampere. And since VGS is 750 millivolt, and in this particular circuit what I have is VDS is 0.8, so naturally MOSFET is in saturation condition. So what I can do is I can just verify what is the current I have. So now it is 100 exponential, okay, 100 10 power 6, okay, sorry, it is micro, it is 10 power minus 6 into 50 into, so since it is 0.75, I can make it as 0.35 whole square equals, you can see this is what is the current. You can see 612.5 microampere, which is the current I got it. So this is ID, which is representing here, so with a VGS of 0.7. So MOSFET is in saturation condition. Suppose if you measure it here, so what I'll do is I'll just go back here and then try to measure it here. Maybe if you can measure it here, so what is the voltage? VGS is, of course, what is VGS? VGS is 1.14232 volt. The current is 2.755 milliamperes, and we know that VDS is kept at 0.8 volt. Suppose if you just see what is this, so these are the specifications of that particular reading. VDS is 0.8, this is this. Suppose if you see this is a value of VDS such that it is in saturation condition, so what should be your VDS? VDS should be greater than VDS SAT. So what is VDS SAT? VDS SAT is 1.142 minus 0.4, which is now, it is 1.142 minus 0.4 is 0.742. So since the value of VDS is more than this, this current should be the saturation current. If I use a saturation current equation, that is 100 exponential minus 6 into 50 into, now it will be 0.742 whole square. That's what is the current. Can you see here? This is 2.75. This is 2.75 milliampere. This is what I'm getting. You can see it is 2.75 milliampere. This is 2.75. So now let me just slightly increase. Let me go over here somewhere. I just try to make the MOSFET in linear region. So you can see now it is, okay, let me make it at 1.42. So let me just take the readings. VGS is equal to 1.421, whereas ID is 4.97 milliampere. What is the VDS? It is same, it's 0.8. Now coming back to this, now VDS is 0.2, so what should be a VGS? Sorry, a VDS SAT. With this as VGS, VDS SAT should be equal to 1.02 volt, but you have a VDS of 0.8, so this current is in linear, so this should be a linear current. if I just go back and verify, so this should be almost tallying with this particular reading. So what I'll do is 100 exponential minus 6 into 50 into 2 into it is 1.02 into 0.8 minus 0.8 square. 0.8 square. 0.8 square. This is expression. You can see it is almost 4.96. So I'm getting okay, this is my current using this equation, which is indicating it's a linear region. Why it's linear region is because VDS at is 1.02, whereas your VDS is less than this, so MOSFET is in linear region. You can see the current I'm getting calculated is 4.96. From simulation it is 4.97. So they are perfectly matching. Now this way we can be able to see the characteristics of the MOSFET. Now we will see one more interesting phenomenon of the MOSFET, which is channel length modulation. So in this channel length modulation, we have the concept of effective channel length. So what happens is this what is that output characteristics, which is nothing but VDS ID versus VDS for a given VGS. So ideally it was coming like this. So it was going linearly and then it was being saturated. So this current was saturated after VDS add, but actually now what happens is, because of channel length modulation, after VDS add, this current slightly increases. This is due to channel length modulation. Now this increase in the current, the drain current with respect to VDS for a given VGS should be represented in the equation also, which is now being represented as ID is equal to half Kp W/L VGS minus VTO whole square 1 plus lambda VDS. You can see, does your drain current keep increasing with respect to VDS? So it is keep increasing, slight increase. So that's why you can see this saturation current is no more independent of VDS. Now it depends on VDS. The unit of lambda is in volt inverse. Usually typical values of lambda is like, okay, 0.1 volt inverse, 0.01 volt inverse, 0.02 volt inverse. This is the typical value of lambda. So we shall again redo the same thing in this particular circuit. Let us find out what is ID in different, okay, especially in the saturation region, with this channel length modulation included. So let me again go back to same circuit. Now let me do output characteristics. For that output characteristics, I'll keep this constant, I'll keep the VDS. So I'll change the variation here. So this will become V2. So let this be fine. So even you can just go up to a larger voltage, make it as 2.5, so that you can see the variation. This is done. You can see that has been modified. And what I'll do, so this impact of channel length modulation, which is this lambda, has to be represented in the model file also. That is coming over here. So in the model file, I will edit that to include that effect. LAMBDA is equal to 0.01. If you want to know exactly what this means, maybe you can see that as, of course you have to be very careful with this. LAMBDA, the lambda spelling has to be proper. So if you can see the same thing over here in this help, of course you can just see that. You can see MOSFET. Okay, in this MOSFET, I think you can get this, all the information. See here, this is lambda, which is channel length modulation, which is 1 over volt. Of course by default it is 0. For example, it can be 0.01. This is 1 over volt or volt inverse. So we should edit the lambda value in the model file so that you will have the effect of this channel modulation felt on the device. Now, since I'm doing dot DC, that is sweeping this voltage from 0 to 2.5, so I should be expecting a graph something like this which just keep changing. So now let me just do it. Now since it is already there in dot DC, I can run this. You can see now you have that variation. Can you see? Suppose if I take out this cursor, okay, now I can see the current changing here. Can you see the current is 200 microampere? Can you see the current is keep changing, 201, 202, 203, 204. This is a small change in the current, which is because of increasing the value of VDS and in presence of lambda. So let us take a particular value of VDS and ID and lambda. Let us verify that. So I have a current of, so let us see what is VDS is 1.28 volt, ID is 202.5 microampere, of course VGS is 0.6. So these are the specifications that I have now. So these are the specifications. Of course I know that this KP is 200, this WL is 50. So let me plug in these values and then find out. So it is now 100 exponential minus 6 into 50 into, why it's 100 is because this half into 200 into VGS is 0.6, it will be 0.2 whole square multiplied by 1 plus lambda is 0.01. This is okay, 0.01, sorry, this is okay, 0.01 into VDS is 1.28. Close the parenthesis and then equals. Can you see the current is, this is a current 202.56, which is 202.5. So this is now, this is the simulation result. So we have a calculated result as 202.56. If lambda is not there, then this will become 200 microampere if lambda is 0. Suppose if you take out this, suppose if I eliminate that, so what I'll do, I'll just go back here. What do I do? Okay, let me just, okay, I'll just, okay, this is fine. This is 100 exponential minus 6 into 50 into 0.2 whole square. That's what we calculated as 200 micro. This way we can see the parameters of the MOSFET. And let me also show you one more interesting thing in the schematic. Whenever you do this, okay, let me just do dot op and then find out. Let me keep this in saturation condition. What I do is okay, let me do dot op and let me keep this voltage as, okay, as I mentioned, 1.28, and if I do dot op and if I run it, can you see I have a current of, okay, 202.56 microampere. Okay, this is your values. See one more interesting parameter, that is go to view and see this here. This is in the error log. You will have all the parameters of the MOSFET being encapsulated. You can see the approximate current is, of course it is approximating as a 2.03, that is 203 microampere. Can you see this one more interesting thing, GM, transconductance, and you can see one more parameter which is GDS. So let us try to find out what is this GM and GDS. So GM is nothing but the transconductance parameter of the MOSFET, which is given by the expression. So now GM, the transconductance of the transistor, is given by 2ID Kp into W by L. So this is one of the important parameters in the analysis of MOSFETs. and this GDS is nothing but 1 over R naught. That is conductance between drain and source, which is nothing but 1 over the drain. Okay, that is MOSFET resistance. If you can find out this, theoretical value of this R naught is 1 over ID into lambda, which we'll be deriving in the theory classes. This is the GM value. Now these are the theoretical equations of R naught and GM. Let us verify the theoretical values with the simulation result. Suppose if you substitute the parameters here, so what I have is under root of 2 into ID is 202.56 exponential minus 6 into Kp is 200 exponential minus 6 into W bell is 50. That's done. So I have a this of 2.01 millisiemens. So this is the unit of transconductance is Siemens. It is 2.01 millisiemens. And coming to this, okay, this is as per our calculation, it is of course 202.56 exponential minus 6 micro, that is 202.56 milliampere multiplied by 0.001 is answer. 1 over that is my R naught. So my R naught is, if I just do it, it is 493.68 kilo ohms, because this is a resistance, so this is the resistance value. Let me find out how much is my GDS from the calculator, from the simulation. From the simulation we found that there is that. Let me just go here, view error log files. Can you see this is GDS, which is 2 into 10 to minus 6. So GDS is 2 microsiemens. 2 microsiemens. So 2 microsiemens to exponential minus 6. 1 over that is 500. Can you see this GDS, which is, okay, sorry, this is this much, and 1 over that is, so if you want to write what is R naught is equal to 1 over GDS, this is this, then it is 500K. Can you see? Okay, let me just one minute. This is what I have. R naught is 1 over GDS, so GDS value is this much from simulation, and we have this as 500K. Can you see this 500K and 493K are almost same? So this is GDS value will indicate what is my R naught is. What is my R naught. So while doing simulation, we can able to find out other parameters of the MOSFET, like what is the transconductance, what is the R naught value of the MOSFET, using this error log file. Okay, in the coming videos we'll see how does this MOSFET will be used as an amplifier. Thank you.